Welcome back, everybody. So we are in the second part of the 3.3 notes here. So last time we defined relative minima and maxima, and now we'll look at some examples. So we'll first start with number one, find the relative extrema of f of x equals x plus 2 sine x on the interval 0 to 2 pi. So we'll start by taking the derivative. So f prime of x is going to equal 1 plus 2 cosine of x, and we'll set that equal to 0. So we're only interested in relative extrema, so we're not going to be looking at the endpoints here. We'll just be looking at our critical points. So then this equation is going to simplify to cosine x equals negative 1/2, which means that x is going to equal, looks like 5 pi over 6. Oops, sorry. 2 pi over 3 and 4 pi over 3. So those are going to be the second and third quadrant angles that will give us cosine is negative 1/2. So now we just need to test those values on our number line. So we've got 2 pi over 3 here, 4 pi over 3 here. And again, we're going to test that with our original derivative expression. So we can look on the left and think about 0. So cosine of 0 would be 1, which is going to give us a positive value. In between 2 pi over 3 and 4 pi over 3 is pi. So if we plug in pi, we'll get negative 1 for cosine. So it'll be 1 minus 2, which will be negative. And then again, we could test 2 pi to the right, and we'll again get an increasing value. Again, these are describing f prime of x. So now we just need to write our explanation. We can see that we're going to have a local max at 2 pi over 3 and a local min at 4 pi over 3. So let's go ahead and write our explanation. So there is a relative max at x equals 2 pi over 3 because f prime changes from positive to negative at x equals 2 pi over 3. Okay. And then for this, the second one, I'll write a slightly different version of this that might be something that you prefer. So we can say that there is a relative min at x equals 4 pi over 3 because f prime of x is less than 0 on 2 pi over 3, 4 pi over 3, and f prime of x is greater than 0 on 4 pi over 3 to 2 pi. So we could also kind of explicitly discuss the increasing and decreasing behavior using inequalities as well. And so either one of these explanations is perfectly fine to use. I find that the first one is just a little bit quicker. It's easier to write, whereas this one is a little bit more formal and kind of a little bit more elegant, I guess, than the first. But again, you can use either one. All right. So number 2, we want to find the relative extrema of f of x equals x squared over x squared plus 3. We're not given a domain, so we'll assume the domain is all real numbers here. Since x squared plus 3 will never be 0, we don't have any vertical asymptotes. So this function is going to be continuous everywhere. So let's go ahead and get started. So we've got f prime of x is going to equal low d high minus high d low, denominator squared below. Again, the denominator is never going to be 0, so that's not going to be as important to us, but we'll keep it in our work until we simplify our numerator. So we've got 2x cubed plus 6x squared minus 2x cubed, it looks like, all over x squared plus 3 squared. So we can see that we're going to get cancellation of those cubic terms. So really, we just get that 6x squared is 0, which means x is equal to 0. So there's only one critical point in this case, which is nice. So we've got 0 for f prime, so we can test two values like -1 and 1. So what we'll see here, though, is that if I've got, oh, jeez, simple mistake. I squared when I shouldn't have. Sorry, this is not 6x squared, that is 6x. Otherwise, we wouldn't have a minimum or a maximum. So again, -1, 1. So we'll get clearly 6 times -1 will be negative. The denominator is never negative, so we don't have to worry about the denominator. And then we'll get a positive here. So we're going to have a relative minimum at x equals 0. Okay, so then I can write a quick justification. So there's a local min x equals 0 since f prime changes from negative to positive at x equals 0. And we can see that for this graph, if we took the limit as we went to infinity, we'd get 1. So our horizontal asymptote is 1. So our graph, oops, we didn't check concavity, so we don't know what the curvature is. But essentially, your graph's going to look something like that. Okay. So let's go ahead and move on to 3. So 3, again, we're going to kind of include where the function is increasing and decreasing, but still find relative extrema. So we've got a polynomial, we've got a trig function, and the trig function we're actually going to have to put on a closed domain. So let's go ahead and put that from 0 to 2 pi. And then we've got that last example, number 8. All right, so for number 3, let's go ahead and start with A. So we've got f prime of x. And I wouldn't recommend multiplying it out. You can if you want to. We can just use the product rule and then simplify. So if we take f prime of x, we're going to have 2 times x plus 2 times x minus 1. The chain rule is just going to give us the derivative of x plus 2, which is 1. So don't have to worry about that. And then plus the derivative of x minus 1 is just 1, so we get x plus 2 squared. So again, we're going to set that equal to 0, and then we'll do a bit of factoring. So we have an x plus 2 that we can factor out to begin with. So we'll factor out x plus 2, and we'll be left with 2 times x minus 1. So that's going to be 2x minus 2. And then that leftover x plus 2 plus x plus 2 equals 0. So let's go ahead and simplify completely. So we'll get 3x. 3x. Interesting. So it looks like we're going to get x equals 0 and -2 as our two critical points. And then we can go ahead and test. So we've got -2, 0. So we can test -3. And again, you can do that with the original derivative expression up at the top or the factored version, either way. So if we plug in -3, I think we're going to get a positive number, yes. So we're going to be increasing here, and then -1 is going to be decreasing, and then positive 1 is going to be increasing. Note that's describing f prime. So now for these, we'll include a little bit of everything. So we'll note that f is increasing on negative infinity to negative 2, or from 0 to infinity, since f prime is greater than 0. F is decreasing on negative 2, 0, because f prime is less than 0. And then there is a relative min at x equals 0, since f prime changes from negative to positive, x equals 0, and there is a relative maximum at x equals negative 2, since f prime changes from positive to negative at x equals negative 2. Okay. And if we think of this graph, right, it's a cubic function, and we know the zeros are at negative 2 and 1. And so we have a positive leading coefficient, so we know our end behaviors are going to be approaching opposite infinities. Maybe I'll move this one over a little bit. And we have a multiplicity of 2 at negative 2. So that's going to give us that bounce, that parabolic sort of shape, since it's degree 2 for the multiplicity. And that's our local maximum. And then from our derivative, we know that at 0, that's our local minimum. And then we'll continue increasing. So that's going to be what our graph looks like. So again, referencing the graph is going to be useful in some cases as well. All right. So now we've got cosine of x, sine of x plus 5. Let me close off that portion. All right, so let's go ahead and take the derivative. So we've got f prime of x. So we'll take the derivative of sine first. So we'll get cosine squared plus the 5 is just going to be 0, so we can ignore that. And now we'll take the derivative of cosine, and we'll get negative sine times sine. So cosine squared minus sine squared. And you can continue to work with it in this form, but I'm really going to highly recommend rewriting it using either an identity or using an identity. So there's two options that we have. We could rewrite this using the Pythagorean identity. So maybe we do like 1 minus sine squared for cosine squared minus sine squared equals 0. So you could do it that way. You could also, if you recognize it, note that this is also cosine of 2x. And it's a double angle identity. So either way, either using the Pythagorean identity or the double angle identity, I think I'll use the double angle identity instead of the cosine squared. And that's going to equal 0, of course. And so that means that 2x is going to equal all of the values that are going to give us cosine of 0. And note, since it's 2x, and my chosen interval was 0 to 2 pi, we can just make a note here that for 2x, we're going to consider all solutions from 0 to 4 pi. Oops, for 2x. So then we're going to end up with 2x equals our cosine of 0, which is going to be, looks like pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And then we'll divide all of our solutions by 2. So we get x is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, which are all of our 45-degree angles. Okay. And I'll let you do the number sign work for the derivative here, and then you can write your solutions for it. And then for 8, also, I think I'll let you do on your own. But note we're given the derivative graph. So on what intervals is f increasing in y? So this you can, again, use a number line test for. So check the notes online for those solutions. And if you have any questions, again, shoot me an email. Otherwise, come by the office hours. And that concludes lesson 3.3.